Good day. If you are watching this, I suspect you are serious about seeking means to a cleaner energy future. A key to that future involves creating practical means for energy storage. This is the core mission for ezNG solutions. It is well known that the push toward intermittent power actually increases the need for natural gas. And we know that LNG will play a huge role for consumers generally wanting greener fuels. However, there is real pressure to find cleaner alternatives because many people realize that LNG has a large carbon footprint. Still, it is expected that LNG demand will double by 2040, and we often see that expanding natural gas markets have a need for local storage. Many parts of North America must depend on surface storage, usually in pipelines or as LNG. The big chill in Texas in 2021 has highlighted the value of having storage close to power generation. In addition to onshore and at-shore storage for power generation, ezNG will support the shipping industry's drive to adopt cleaner fuels, starting with LNG. So let's look at ezNG's cold liquid storage technology, where pressurization forces are balanced by adjacent cells. Low-cost, mass-produced cells can efficiently fill available storage spaces. Cell arrays in reinforced structures safely store LNG at low to moderate pressures. On land, cells are secured within insulated concrete vaults. For the maritime industry, much larger cells can fill insulated cargo holds in ships or barges. To store fuel on ships, GTT has proposed its low-pressure LNG brick tank concept. This independent prismatic tank involves complex manufacturing. The German tank manufacturer TGE has recently provided marine fuel storage using big pressure-competent cylinders. An ezNG fuel tank can be designed to hold just as much LNG at the same or higher pressure rating while occupying less hull space. The cell array can be segregated into 2 tanks if desired. Only 5 flasks are needed in the array if the cells are made as tall as TGE's big cylinders. This slide introduces ezNG's alternative to the LNG fuel bunkering barge being built for Polaris. ezNG cells are much less costly than big vacuum-insulated bullet tanks and can be fabricated locally instead of being imported from China. Further, ezNG's cells for LNG cargo storage require much less internal hull space, so the barge can be smaller, or wing tanks can be included along the length of the hold to reduce risk of cargo release in case of a collision. Most power developers will want storage permanently secured nearby the power plant. ezNG has been working with a major U.S. pipeline owner to address supply pinch points on their system. While we are constrained from revealing details, key features of this simple concept are obvious. This barge can receive LNG from a matched liquefaction facility onshore or delivered by a bunkering barge. While we know ezNG can cost-effectively serve the needs of a growing LNG market, we are excited that our technology opens the way for cleaner options. Many companies and countries are already looking for carbon-free fuels, and because it is a very dense hydrogen carrier, green ammonia is likely to be a real game changer. The EDF has already concluded that ammonia is the best option for maritime fuels long term. However, while the world produces, transports, and uses huge amounts of brown ammonia today, it will be decades before adequate supplies of green ammonia are available. Nearer term, there's pressurized LNG. PLNG was invented over 50 years ago as a sweet spot for liquefying natural gas for global transport. This graph shows how PLNG avoids costly high-pressure CNG tanks on the right, as well as the high energy needed to produce conventional LNG on the left. In fact, ExxonMobil says that LNG requires twice as much energy as PLNG. Unfortunately, there were two big problems back then. First, there was no practical concept for storing large enough quantities for ocean transport. And second, prices for natural gas fell so much that the LNG industry collapsed for years. Pressure-competent storage allows adoption of both ammonia and PLNG as fuels for the energy transition. But one might ask, the LNG industry has been going strong for many years now. If PLNG is so great, why hasn't it already displaced LNG? 25 years ago, ExxonMobil thought PLNG was attractive enough to invest many tens of millions into R&D. Here's a summary of the key advantages Bowen reported in 2005. Pretty impressive, eh? So why did ExxonMobil drop the ball? One can guess that PLNG was competing against its own megascale LNG projects. So the ship for this very special remote project was designed with a very large capacity, much more than typical for LNG carriers of the day. And the big cargo storage cylinders were a problem. Their patented high-strength steel and welding required intense R&D efforts, and it would be very costly compared to commonly available cryosteels. It was also an expensive challenge to secure these tall cylinders into the ship's double bottom. Further, tanks made of this material were not even able to transport common LNG. Around 2005, the PLNG initiative was shelved. What we have discovered is that ExxonMobil and the world needed a simple and efficient, pressure-competent tank technology. Due to the high cost of ExxonMobil's very special steel and welding, as well as the unique ship design with cylindrical supports extending into the inner bottom, their ships would have been very expensive. In this rough design comparison, the ExxonMobil PLNG carrier is estimated to require about 5,000 tons more of very expensive steel for containment. Further, it is easy to see that ezNG's design would be much smaller. Therefore, it is expected that each ship would cost about $150 million less. That represents huge savings in projects involving several ships. Another big advantage for ezNG ships is that they can carry either PLNG or LNG. Now I should point out that PLNG is only about 80% as dense as LNG, so to deliver the same amount of natural gas, the tanks need 25% more internal volume. Still, this slide indicates how the right tank technology allows a switch to the much greener PLNG while getting more than twice as much of the fuel into a vessel just slightly larger than the Polaris barge. Let's take a moment to consider a favorite option of many folks promoting a carbon-free world. Battery storage facilities are being deployed today, with an expensive 100 megawatt system already set up in California. It is probably no surprise to this power form that LNG storage is much cheaper than the battery option. However, please note that the PLNG option is even less costly and will produce about 100,000 tons less CO2 than the LNG option over a 20-year life. As highlighted by the previous slide, most popular decarbonization initiatives result in much higher costs for energy. For example, CCS is a very complex and costly option. So it is important that we find and adopt ways to reduce CO2 output. We know that natural gas is a great alternative to coal and oil-based power gen. We also know that intermittent energy sources need storage media to have any viability. Therefore, the world will continue to seek liquefied natural gas for low-cost, cleaner power throughout the energy transition. However, now that a practical containment technology exists, the industry should focus on PLNG as the way to reduce both costs and CO2 output. Our low-carbon future depends on practical means for energy storage. Because PLNG is simpler and costs less than LNG, it provides a great opportunity, not a burden, for reaching your carbon reduction goals. Thank you all.